All right, so questions? Yeah.
Well, I was just wondering, so I was working on PA2 and file grind, it seems like I have a lot of memory
Okay.
leaks in the program. I was just wondering where should I release all the structures that I create in the add function at the end of the add function?
You can't do it if it's temporary, you should release it, but if you're actually malloking a node to add to your list, you can't release it. Otherwise, when you go to print, for example, it won't be there.
Okay.
So at the very end of your program, when the person says exit, before you actually exit from your main program, you want to call a function that goes through your list and frees all the memory. And you can do that by, here's your list. This is your Sentinel node. Let's say you got 3 nodes plus a Sentinel. So how do you release all the memory? Temp equals list. Temp2 equals list next. So this is temp2. And then free temp. So this node has been released from memory. And now I need to move down to this point, so I'm just going to say temp equals temp2. And I'm going to go back up here. So temp is this node. Temp2 is the thing that it points to. And I'm going to free temp that releases this node. Back to the top of the loop. Temp is what temp2 was. Temp2 is the next node. Free temp. That one's gone. Back to the top of the loop. So temp2, sorry, down here, temp is temp2. Back to the top of the loop. Temp2 is whatever this is pointing to, that's null. Free temp, back to the top of the loop. If I do this again, I'm sorry, I keep forgetting this. So temp equals null. Come back to the top of the loop. If I do this, I'm going to segfault because temp is null. So this whole thing can be a while loop while temp is not null. And when you kick out of that, all your nodes should have been released. You return, and then your main program can exit. Mm-hmm. Temp, yeah. Thank you. That's one of those where I'm writing something, but I'm thinking something else. That's the thing that's hard to debug. So I'm mic'd up, by the way. Yay. So, and it's apparently really good because I can walk over here and it's still picking me up. And I don't know if I can go in the back of the room. And I think it's still picking me up there. But this probably sounds really choppy on the audio. But anyway, so we'll see how that works. All right, other questions? How's the ODP? No issues on 209? No, there's no my null. It's just null uppercase letters. That's defined in standard I/O. ODP 209, which went live this morning, you're given the address of a linked list, and there's no Sentinel node. although that doesn't really matter. But you're given a pointer to the first node of the list, and your goal is to delete this middle node. So you've got the address of this first node. Your goal is to change this to point to the thing that that second node was pointing to. You don't need to free this node. You can if you want. I'm not checking that. But you're trying to adjust pointers. Okay? It's not a general delete routine. It's not PA1 or PA2's delete routine. You don't know anything about the values of the data in these nodes. So you can't just write your delete routine inside here and delete that value because you don't know what that value is. Your goal is to manipulate these pointers by hand, right? Write some code that takes this pointer and changes it to point to that. Okay, classic exam question, classic interview questions. Being able to manipulate these pointers. So that's ODP 209. The next one, which I'll post tomorrow morning, we'll have you insert into a list. So same idea. You'll have a list, and I'll ask you to insert something between, say, the second and third node.
I just realized I did this one already,
Mm-hmm.
and I just realized I did multiple lines to be like previous, middle.
Yeah, yeah.
When I could have just done the arrows. But
You can do it with just arrows on one line, but you can also use temporaries, and either way is fine. All right, so stacks and queues. Starting with stacks, we're going to try to get through all of stacks today and then do all of queues on Wednesday. Well, not all of, but the stuff that I want to go over for stacks and queues. So we already motivated the idea of a stack, right? It was this pile of plates. You add a plate to the top, you remove a plate from the top. The whole access is through the top of the stack. And the last thing that you put on that pile is the first thing you pull off. So that was the basic concept. So let's formalize this a bit. So we have a notion of push. And we'll deal with integers today, but you can push anything. You can have a stack of anything. You can have a stack of strings. You can have a stack of characters. You could have a stack of functions. You could have a stack of linked lists. Okay, it doesn't matter what the thing is. But whatever the thing is, when you want to add another thing to the stack, you could use a function called push. And the flip side of that is a function called pop, which removes whatever the last thing was that was pushed and gives it back to you as a function value. So you could do, you know, n equals pop. And we probably want some sort of initialization routine to create an empty stack, because they don't just exist when your program starts running. So we want some way to create an empty stack. I'll just call it a init. And there's two conditions we'd like to know when they occur. One is if the stack is full, and the other is if the stack is empty. So is full will tell us if the stack is completely filled up, meaning that if the stack's full and we try to push one more thing, we'll get an overflow. That's an error condition. Is empty says, is the stack completely devoid of all objects? And if it is empty and we try to pop, that's an underflow. It's an error condition. So is full, is empty tell us not to push and pop when we shouldn't. Init creates an empty stack, push stores something to the top of the stack, pop removes from the stack. Straightforward. All right, so how do we implement stacks? We can use arrays. We can use a stack pointer. We can use a linked list. we could use magic dust. There's a lot of ways we can implement a stack. But up here, the user view of a stack is just this. Push pop init is full is empty. Okay, it could be other things, but we'll just stick to these 5. That's how the user, your main program, for example, interacts with the stack, is through these things. The implementation of the stack might have an array, and it might have something called a stack pointer that we initialize to 0. And when we push, we store in the array where the stack pointer is, and we increment the stack pointer. And when we pop, we decrement the stack pointer, and we pull off from the array. But we might switch to an implementation that uses magic dust, right? And if we switch from using arrays to magic dust, we don't want the user to have to rewrite their code. So this is the idea of an abstract data type. An abstract data type means that we present to the user an interface to the data structure, a collection of routines that they call, and a description of what those routines do. And that's the only thing we expect or allow the user to know about the stack implementation. The user says push 5, and they expect a 5 to be sitting on their stack, such that if they now say pop, they get back that 5. And if they push 5 and push 7 and then say pop, they expect to get the 7. And if they pop again, they expect to get the 5. And they don't care or know if you're storing that 5 and 7 in an array, if you're building a linked list containing 5 and 7, if you're doing something totally strange, if you're sending a text message to some grad student somewhere who's writing these things down on a whiteboard, right? It won't change the user's code if you change the implementation. That's the idea of an abstract data type. So this view of a stack, this is an abstract view, abstract in the sense that it's devoid of these implementation details. Okay, and everything I want to talk about the first half today is looking at abstract stacks. And then the second half, we'll talk about implementing them. That's when we'll get into these details. Okay, but all our data structures, we always want to keep in mind this division. As an abstract data type, what does this structure look like? What is a linked list? Well, it's a thing you can insert a node, you can remove a node, you can tell if the list is empty, you can delete a node, you can print the nodes, right? Is the list singly linked? Is it doubly linked? Is it circular? Is it, something else? That doesn't change your view of what a linked list is. All right, so why do we care about stacks? Well, first of all, we use stacks in our daily life, in our head, right? When we're going about our day, things interrupt us. And we usually try to remember what we were doing before we go off on a tangent to do something else. And we actually generally use a stack-like structure to do that housekeeping. So here's an example. So let's say you're making dinner. So you start getting the ingredients, you start chopping your vegetables and so on like this. And partway through, you get a phone call. Okay, you stop what you're doing, you've got the onion half chopped, you leave it on the cutting board, and you pick up your phone. And you talk to somebody, and they say, hey, can I borrow your physics notes? And you say, sure, I'll bring them right over. So now you go to your friend's house, and you hand them your physics notes. And when you get there, you notice that they're playing whatever your favorite game is. I was going to say something, but yeah. So they're playing a cool video game, and they're like, hey, thanks for the notes. You want to play some games? And you're like, sure, okay. So now you play video games. And you do that for about an hour, and you notice you're getting hungrier and hungrier, like I should get back to my dinner. Okay, so you're done playing video games. You remove that from your stack. What was I doing? Oh yeah, I was at my friend's house. Okay, I'm done with that. I'm going to remove that. I'm going to go back to where I was, which was my phone. So you go back and you get your phone and you hang it up, because you work very literally that way. And now you're ready to start making dinner, except that you realize you forgot to get the mail. So you go outside and you get the mail, and there's your paycheck. So you want to open that. So you open the mail, and it's a really big paycheck, and so you decide to buy something. So you go to Amazon, and you're done with that. So you pop that off, and you're done reading that mail, and you go back and you look, and there's another thing in the mailbox, which is a bill. So you get that out and you pay, right? So you get the idea, right? So eventually you're going to get back to where you were making dinner, right? And before you started making dinner, maybe you were doing homework and you got hungry, so you started making dinner. So you're done, you pay the bill, you finish getting the mail, you go back to making dinner, and you finish that, and now you go back to doing your homework. So we tend to process things in the stack-based way, right? And when something interrupts what we're doing, we save what we were doing somehow, somewhere, so that when we're done with that interrupt, we can come back to where we were. But we might get interrupted 5 more times while processing that interrupt, and at some point, we come back to the last thing that interrupted us, and then we come back to where we were. So the latest thing that you push onto the stack is the first thing that you're going to remove from the stack. Okay, so it's that whole LIFO, last in, first out. And this is what computers do, right? This is how function calls work. So fictitious programming language, so with line numbers, code used to have line numbers on it. Go figure. So line 100, you do something, and then at 110 you say call function 1, and at 120 you do something, and at 130 you say call function 2, and at 140 you do something, and so on. And function 1, let's say it starts at line 200, and the first thing it does is call function 2, and 210 does something, and 220 returns. And function 2, let's say it starts at line 300, and it does something, and then it returns. All right, so you start off with an empty stack. Now, when I drew my stack up here, I grew my stack in this direction on my page of paper. That's arbitrary. Okay, so here I'm going to grow my stack in this direction from bottom to top. Don't fall in love with one way versus the other. Okay, it's just this idea of adding and removing. It's not oriented to some particular thing. So let's suppose we start executing this code. We get to line 110. It's a function call to fun1. When we finish executing function 1, we need to come back to line 120, right? So we push a 120 on the stack, and then we go down to function 1. Function 1, first thing we do is we say call function 2. When we get back from that call, we need to come to line 210, so we push that on the stack, and we go to function 2. And we execute whatever line 300 is, and here's a return. Where do we return to? We pop the top value off the stack, and we go back to line 210. And in doing that, we've preserved where function 1 is going to return to, which is line 120. Now, if we had another call to function 2 right here, we would save the address that we're supposed to return to, which is 220. We'd go to function 2, we'd do line 300, 310 says return. We pop off the top of the stack and go to that address. That brings us back here. There's another return. We pop off the top of the stack is 120. This is where we return to. So stacks are used to handle calls and returns. If you've taken 270, there's a small stack inside the PIC processor, and there's push, and there's pop, and there's a bit in the stack pointer register to tell you if the stack's empty or full, right? So exactly the same mechanism here. And pretty much every architecture has a stack in it that's used for doing function calls. And this also is how interrupts are handled, right? Like our example of the person making dinner. Because an interrupt's really just an unscheduled function call. But just like a regular function call, save the address of the next instruction, go deal with the interrupt. And if you get interrupted in the interrupt routine, save the address of the next instruction, go to the interrupt. And those saves are just pushes, and your returns are pops. So stacks are good for managing all of this call and return gymnastics. They're also useful for local variables. So here's, let's say, function 1. And it's got 3 integers, a, b, c. So in C, when you define a variable inside a function, it's got a scope, right? The scope of that variable is limited to how long that function is executing. When that function finally says return, those local variables disappear. And if you come back into the function and you check the values of those, they're not going to be the same as they were when you exited. They're purely local. So here's our main program. And let's say it does a call to function 1. And so down here, 200, there's some stuff. All right, so let me draw a stack, and we'll grow upward. So we start off and we say call function 1. So we want to save the address of the next instruction to execute when we return. When we get into function 1, here's what's going to happen. The compiler will have created code which does the following. It basically pretends that there are 3 things added to the stack. And this becomes the new top of the stack. And what it's doing is it's setting aside space in the stack for your local variables. So now when I say a equals 5, it stores a 5 down here. When you say b equals 7, it stores a 7 here. But it's actually using memory inside the stack for local storage. Now the advantage of that is when you say return, there's also code that's been put in there to basically change the top of the stack to look like it's right here. So now when you say return, top of the stack has a 120, you pop that off, you come back to location 120. Those local variables are still on the stack, but since your stack looks like it's empty now, other things will take advantage of those locations in memory. They'll either be used for more local variables or call return addresses or whatever else you're using the stack for. So stacks are useful for local storage. And when we start talking about recursion, this will be critical. Because you could just as easily say, okay, function 1, you're going to store A at location 500, B at location 510, C at location 520, right? Well, the problem with that is that if function 1 calls itself, the second version of function 1 is going to store A, B, and C at exactly the same locations that the first version did. Locations 500, 510, 520. And so when this second version of function 1 changes the value of a variable and then returns, the first version's variables have been altered. If you save your variables, your local variables on a stack, each time that you call, you get a separate location in memory to store your local variables. And it won't disturb the values that you had in the caller. So we'll talk about recursion in a few weeks, and this will make more sense then if it's fuzzy here. But just sort of mentioning it as a motivation for stacks. All right, we can also use a stack for maze running. And when you solve a maze, what do? You start at the entrance and you get to a decision point and you can go left, straight, or right, let's say. So you say, okay, I'm going to go left, and you see where that gets you. If it gets you to the exit, you're done. If it gets you to another decision point, then you say, okay, well, here I think I'm going to go straight, right? And eventually, if you've explored all the possible decisions that you could make after that first turn, and none of them have gotten you where you wanted to go, you come back to that first turn that you made and you said, okay, I guess going left wasn't the right choice. I'll try going to the right, right? And so you have to keep track of all these different places where you've made a decision, so you can do this with a pencil or something if you're actually doing a maze. But you can do that with a stack in a computer. So let me draw this a little differently. Let's start off with the entrance to the maze A. And let's say we've got 3 possibilities. So I'll number these 1, 2, and 3. And let's say at this point, so think of roads between cities, like in a forest or something, so you can't see ahead. So here's point B, and let's say there's 2 paths that you can follow. And let's say here's point C, and there's only 1 path you can follow. And here's point D, and there's 2 paths there. And let's put a 3rd path here. We'll call that 3. You don't have to make a copy because I'm not going to use most of these. And let's say that right here is the thing you're trying to find, the exit to the forest, or the pot of gold, or whatever it is. And we'd like a way to systematically explore all the possible paths we can take so that we eventually find the way that leads us to our target. Well, let's use a stack. So I'm going to grow my stack from top to bottom just because I got space up there. And when I'm drawing these stacks, right, if I push an A and I push a B and I push a C, then I pop off a C and I want to push a D, I might write it over here or I might write it down here, right? Don't get tripped up by that. This is a very informal way I'm using of representing what's on the stack. But if I don't have space to go out sideways, right, I might put it underneath. It doesn't mean anything. All right, so how can we run this maze systematically? Well, we're starting at point A, and we have 3 choices. We can go down branch 1, 2, or 3. Okay, I'm going to start off by just going down branch 1. I'm always going to go down the lowest numbered branch that I haven't gone down yet. So I'm going to push an A, 1 onto my stack. And I'm going to travel along this edge. And I don't find my destination, but I find another branch point. I get to location B. And I can go down paths 1, 2, or 3. Okay, I'm going to choose to go down the first path, so I'm going to push that onto my stack, B, 1. And I'm going to follow that along. And I'm going to come to another branch point, C. And there's only 1 path coming off of there, but my algorithm doesn't care. I'm going to go down path 1, so I'm going to push C, 1 onto my stack. And when I do that, I get to a dead end. Okay, now I need to backtrack. So I'm going to pop off the last decision point, which is C1. And I'm going to increment my branch number to 2. And I'm going to say, okay, I want to go down path 2. There is no path 2 at C. So I'm going to pop off again. So B comma 1, I'll increment that 1 to a 2. Now I want to go down path 2. So I'm at B, I'll go down path 2. So push that on my stack. Come down B2. Here's another branch point. You got the idea? So every time I come to a decision point, I'm going to pick the lowest numbered path that I haven't gone down yet, and I'm going to push that onto my stack. When I hit a dead end, or when I'm out of paths that I can go down, I'm going to pop my stack. I'm going to increment the number to go down another path. So here I'll push D1, that'll dead end. I'll pop it off, I'll push D2, that'll dead end. So now I've done this and this. So now I'll pop off D2, and I'll try to go down D3. There is no D3. Okay, so I'll pop off again. There's my B2. I have to go back to B, and I already went down 2. Let's try going down B3. So I'll push that onto my stack. I'll go down B3. There's my target. And if there was no target, if you just kept doing this, eventually you would travel along every possible path from A to any dead end. And it's pretty naturally a stack-based structure, right? Because at each point, when we have a decision to make, we need to remember where we were so that if eventually we get back to that same location, we can go down a different path. And we don't need to do anything with location A until we've explored all of these possibilities. And if B3 ultimately didn't work, we'd pop that off. We'd pop off A1, and now we'd say, let's try A2, and we'd start exploring this whole bottom part of our pathways. So we'll see some of this when we do graph theory, and we look at traversing graphs, and this is one way to traverse a graph. This is called a depth-first search. So depth first. DFS. And it's depth first because starting at A, we try to go as deep into the woods as we possibly can. And if that's not right, we back up as little as we have to before we can start going deep again. We back up a little bit and we go deep again. And we only come back to A after we've explored all the possibilities off that first branch. Okay, we can also do, so this is a stack that we use for a depth-first search. We can also do the same thing with a queue, and that's going to be a BFS. A breadth-first approach would say, first let's try going one hop from A. So we'd visit B, we'd visit E, we'd visit F. And none of those had our targets. And then we would say, okay, let's go one hop from each of the things that we already got to. So that would travel along this edge, and 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 this edge. And if that didn't find our goal, then we'd say, okay, let's go a third hop from all the places that we've already gotten to. So that would be, I missed a purple. So that would be that, that, that. Right, so in a breadth-first search, our first pass, we're moving a distance of 1 from our starting point. Second pass, we're moving a distance of 2. Third, we're moving a distance of 3. So we're slowly getting further and further from our start. That's breadth first. Depth first, we just try to go as far down one path as we can. And we back up and keep going further. Right, and that's the way most of us tackle mazes when we have a maze on paper.
Breadth first seems really similar to
Dijkstra's algorithm?
Yeah.
Yeah.
Very similar to that.
Yeah, yeah.
You're moving down like a node at a time, no matter what the branch is at.
Yeah, so breadth first is handy if we wanted to find the shortest path, right? And we do a breadth first search. The first time we reach a destination, that's our shortest path, or a shortest path. Because our total path length grows by 1 each iteration. So yeah, that's stuff from 215. It's all connected. It can be. It gets more interesting when your paths have weights on them. So not all paths from point A to point B are the same. So if you're sending traffic from Netflix, right, from here to this point next to me might be a single hop, but this might be a really slow conduit. This might be, some low baud rate communication like a cellular signal. I might also be able to go over there and then get to my customer, but that's all high-speed fiber. And even though it's 3 hops, it's going to take less time to go along those 3 hops than along this 1 hop that goes through a cell tower. So when you start putting weights or costs on what it takes to travel along each of these edges, and then you say, okay, what's the lowest cost from point A to point B? That's where you get into things like Dijkstra's algorithm, where you can't just look at the number of links to get there. And that gets interesting. So that's all 215 stuff. All right, one more application of stacks. There's a lot of applications of stacks. One more application. So here's an algebraic expression. And the parentheses tell us what order to do things in. This says take 2 and 4, add them. Take 1 and 3, add them. And then multiply. So we should get an answer of 24. And there's a natural precedence to operators. Multiplication comes before addition, for example. But there's also parentheses that say do these things collectively before anything else. And this is the way most of us think about expressions, right? But it's a little bit cumbersome to try to actually take a string containing this and end up with this number 24. Mainly because of the parentheses. They sort of require a lot of housekeeping. But it's the way that we usually think of things. Now here's a different way to write an expression. This is called postfix. It's also called reverse Polish notation. And the idea is you list a pair of operands, and then you list an operator. So this says take the operands 2 and 4 and add them together. And then I would say take the operands 1 and 3 and add those together. Well, this first thing left me with the number 6. This second thing left me with the number 4. And now I want to say multiply those 2 things together. So in postfix, this is the same as this. And I'm showing it with single digits because otherwise you need some way to know if this is 24 or if this is a 2 and a 4. And normally you'd have some way of doing that, but I'm not showing that here. So old Hewlett-Packard calculators back in the 70s, they used postfix for entering in things you wanted to calculate. So if you wanted to do 5 times 7, you'd take a 5, you'd hit a 5, you'd hit the enter key. You'd take a 7, you'd hit the enter key, and then you'd hit the multiply key, and it would say 35. And it's a little unnatural feeling at first if you're used to thinking of algebraic expressions. But pretty quickly, RPN starts to feel really natural. And you just kind of think of equations like that. And you could hand your HP to a friend, and if they didn't know how to use it, it was fun watching them like, what's wrong with this thing? Okay, so this is a different, but in some sense, it can be a natural way to write expressions. It turns out this is really easy to evaluate using a stack. So a lot of times in data structures courses, you write a stack-based calculator. I'm not doing a stack-based calculator assignment, but turning this string or array of symbols into a value is pretty straightforward. So here's how we can evaluate this using a stack. So you start looking through these tokens, okay? So this is a token 2, it's a number. This is a token 4, it's a number. This is a token plus, it's an operator. Okay, so pull off your tokens one by one and do the following. So if you have an operand, push it onto your stack. If you have an operator, then we want to pop twice, apply the operator, and then push. So if you have an operand, you just push it on the stack. When you get to an operator, plus, minus, times, divide, pop 2 things off, apply your operator to them, and push the result onto the stack. Okay, so pop twice. Apply operator, push result. That's what that means. So let's do that for this expression. So I'll draw my stack sideways this time, so it grows to the right. All right, first token we get is a 2. That's an operand. We're going to push that into the stack. Next token is a 4. That's an operand. We'll push that onto the stack. Next token is a plus. That's an operator. Pop off the 2 and the 4. Apply the operator. 2 plus 4 is 6. Push a 6 into the stack. There's a 1. Push that on the stack. There's a 3. Push that on the stack. There's an operator plus. Pop off the 2 things at the top of the stack. Apply the operation. The result is 4. Push that onto the stack. There's another operator star. Pop the 2 things off the top of the stack. Apply the operation. Push the result. We hit the end of the string. Our stack contains 1 thing. That's the value of the expression. And that always works, as long as your expression is well formed. And this will catch syntax errors too. So if you did something like 2, 3, plus, plus, right? We'd push a 2. We'd push a 3. We'd get to the plus. It says pop off those 2 things. Apply the operation. Push the result. That's a 5. We get to another plus. It says pop off 2 things from the top of the stack. We'll pop off the 5. When we try to pop again, we'll get a stack underflow. That means there was a syntax error. If you do something like 2, 3, plus 5, we push the 2, we push the 3, we get to the plus, we pop them off, and we push a 5. We get to another operand, we push a 5. We reach the end of the expression. We have more than 1 thing on our stack. That's a syntax error. So it'll pick up malformed expressions like this. Yeah.
With old calculators, I know that like if you hit like plus a bunch,
Mm-hmm.
it takes like the last input with the result,
Yeah.
and we'll just like you can just keep hitting that, and it'll keep repeating the last
Right.
operation.
Yeah. So old calculators that used algebraic notation, and you could say like 2 times 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 times, and get powers of 2 out, because it keeps multiplied, puts it in what I think they call it constant mode. And if you repeat an operand, an operator, it just used the last operand again. And that's different from RPN. In RPN, though, you could say something like that, and that would give you 2 to the 5th, 2 to the 6th. You could also do this as take 2 and 2, multiply, and then multiply by 2 again. And that's the same expression's value. RPN is quirky, but it works. I still use it. I have some software I wrote. Let's see. When did I write this? I wrote this in 1996. So 22 years old. And for part of it, I was inputting Boolean expressions, and I wanted to evaluate those expressions. And quick and dirty prototype, I decided you got to input your expressions in RPN, because it let me use a stack to evaluate them. I'll go back and change it later. Never did. So 22 years later, it still requires you to put these things in postfix notation. But it works, so why break it, right? If it ain't broke, don't fix it. All right, so that's another use for stacks. And like I said, that's a pretty classic data structures course problem, is to make a stack-based calculator. The question of how do you go from algebraic notation to reverse Polish is a different one. And we'll talk about that later when we talk about trees. But there's some programmatic ways to take this and change it into this. And that's how a lot of expression evaluators actually work. They change it to this internally and then use a stack to evaluate it. All right, so that's an idea of the kinds of things we can do with stacks, right? Stacks are useful enough that pretty much all processors have stacks implemented in their hardware. So PIC processor has a 30, I think it's 30 instead of 31, a 30 element stack built in that you can use, and as part of the hardware structure of it. The operating system maintains a stack that's independent of a hardware stack that's used for local variables and things like that. And there's a lot of variations in how stacks are implemented, but usually they're stored in memory in some form. So we have 2 main ways of implementing a stack. One is with an array, one is with a linked list. And I want to work through details of both of those and see some of the variations on them and so on. So let's take about a 5-minute break, and we'll come back. We'll talk about implementing stacks. And then Wednesday, we'll talk about queues.